Welcome to session number 1 on the physics side. Okay. First of all, we're going to go through elements of the things around us, right? Like we've in chemistry, for those of you who've looked at the chemistry, we're dealing with generally the everyday occurrences, and we're looking to see and explain what is happening around us, right? No, we're not looking to understand what is happening at the center of the sun or the middle of a black hole, etc., etc. We're looking first of all at the elements around us, the wind, the weather, the things falling, things floating. That's what we're looking at this point in time. In the first part of physics, we're going to be looking at waves, sound, and light. Okay. Now they're quite important. This is where we get to play with some more toys than chemistry. Unfortunately, playing with chemicals around here is not the easiest thing to do, but we can play with a few things. Like one of my favorites is the good old slinky spring. Okay. And for those of you who prefer a little more sort of art, we can use the color one as well. Right. Now, first of all, let's look at waves. Okay. Waves. Let's look at a few terms in waves, right? Because we're going to break it down into very simple sort of selection of processes for waves. They're not tough to do at all. Okay. Well, first of all, what is an oscillation? Oscillation, okay, it's a word we find in this topic. It's a movement, right? When something oscillates, it moves, right? Usually about a common point. So a pendulum oscillates. It goes there, to there, to there, to there. So it's oscillating about a common point, the middle, right? A wave also oscillates. It moves, okay? If you've ever stood at the end of a jetty and watched the waves going past, you'll see them, okay? They're moving past you, okay, in the sea, all right? What is a pulse? So let's say oscillation is a movement, okay? What is a pulse? Well, first of all, we need to know, how do we make a wave, right? I can do that, and a wave, can you see I'm pushing it, or I'm doing this, okay? I am taking this end and moving it down. What I have done is I have created a pulse, okay? I have sent one wave down, which is my pulse. It's a push or a pull usually, and it comes from an external force, hands, a magnet, or an electric field, all right? So a pulse, okay, is something that creates the wave, okay? And it can be magnet, electric field. Okay, don't worry, we'll get into all these topics, what magnetic fields, electric fields are, etc. But just for the moment, that it can do that. All right. Right. Now, let's have a look at a pulse, okay? There's two types. One is a transverse, and the other one is longitudinal. Transverse and longitudinal, right? Well, what does it mean, right? Transverse basically is this way, or that way if I'm putting it on the table. I don't know if it's clear, but I'm doing it that way. So it's either up, down, or side to side movement, right? Transverse means either that way, okay, or that way, right? Longitudinal means along. It's this kind of pulse here, all right? So longitudinal, long means along the direction. Okay, so it's going along. Transverse is then the opposite, which is perpendicular at right angles. Okay, well, we're going to get to that now. Okay, all right. What is the word medium? Okay, The word medium. No, it's not how you would ask for a piece of meat to be cooked. Medium here is what is the wave going through. So medium could be air, water, gas, okay, or it could be a solid. For example, a piece of metal, right? You think that's a bit odd, okay? Well, in air is a gas, isn't it? It's a mixture of gases. Sound waves travel through air, right? Water waves travel through water, the waves in the sea. Gas, once again, sound waves can travel through it. A solid, well, it's also very simple. If you take an iron bar, right, and you tap it at the one end, you will hear the vibration at the other end. You'll hear the ringing at the other end. That is a wave that has been propagated along the medium. It's gone through the medium, right? For example, light. Light comes from outer space. Vacuum, nothing. Comes into the atmosphere. There's air. Light goes into water. Otherwise, how can you see at the bottom of your pool? The light actually goes through the different mediums. And we will talk about how it does it and what happens to it when it does it, okay? So we've got, that's the medium, okay? That's what it's going through. Now then there's a few things. Let's have a look at the particle, okay? A particle is a point on a wave, okay? It's a fixed point on the wave itself, right? So there's our particle we're looking at. We're looking at it, does it move this way or does it move backwards and forwards, right? We're looking essentially at the displacement, the movement of a particle, right? Just a fixed point on the wave, nothing more than that at this stage, okay? Let's look at the word velocity, okay? The velocity of a pulse. All right. What is the velocity of a pulse? It's how fast I pushed it, pulled it, or moved it up and down, isn't it? Right. Then what is the velocity of a particle? All right. The velocity of the pulse and the particle we're going to get to, but the particle on its own is how fast is that part of the spring moving this way and that way, or up and down, or side to side. That's the velocity of a particle. It's the actual piece of the wave we're looking at, okay? You can think of it as the velocity of a water molecule as the sea wave goes past, okay? The velocity, it goes up and it goes down, doesn't it? Remember when you're sitting in the sea, when a wave comes, it lifts you up and it drops you down. Lifts you up, drops you down. Just hold on, let's think about that. The wave comes, if I'm here, it's now lifted me up. The wave is moving that way, isn't it? But the wave is going that way and I am going up and down. So I am going perpendicular to the direction of the wave. That's quite an important concept that we've got to come into it. All right? My displacement, okay? My displacement of a particle, I could be the particle, okay? The displacement of the particle, right? Let's just look at this. Here's the sea with no wave. Okay, so that's the level sea. Now all of a sudden, let's change the color. Okay. Now all of a sudden a wave comes. Here it is. Okay. A wave comes in from the sea. What do I do? Which way do I go? Okay. I'm red. I now suddenly go up to the top of the wave. All right. The wave is going which way? It's moving that way. So the velocity is to the right, isn't it? It's moving to the right. But me, I'm going up and down. So if the wave is moving that way, I am moving perpendicular to the direction of the wave. Okay? So I'm moving perpendicular There's the direction. There's me going up and down. Up and down. Because what happens when this wave has passed and the next wave comes and it's down here? Right? Where am I? I have gone down. Right? So the wave passes me. I go up to the top, down to the bottom. Up to the top, down to the bottom. Right? These have got specific names. This is called the crest. This is called the trough of the wave over there. Right? So we've got a crest and we've got a trough. Crest and trough of the waves. Now, what happens if the wave, right? Remember we said that's a transverse wave. What happens if the wave is longitudinal? All right? Longitudinal. Okay? In other words, the wave, I'm going to draw it like this. Pretend this is a slinky spring, and there they're close, there they're far apart again, right? What has the particle actually done? Let's look at our slinky spring, right? Now, let's take a piece. The pulse comes along, pushes it that way, back and back to start. So just like in a water wave, we go up to the top, down and back. We start here, we go up as the wave comes, down as the wave goes, and back. If the wave's going this way, a longitudinal wave, I go forwards, back, and back, right? So my movement, my displacement, okay, in this case is forwards, backwards, and back. Same thing, that's the same as an up, a down, and a back. It's just that in this case that the displacement is in the direction of the wave, right? Because the wave is going this way, it's going that way down the spring, right? The displacement is in the direction of a wave. All right? Right, let's look at some more terms, all right? I'm now going to deal first of all with a transverse wave, one that we see in the sea, all right? Here we go. Let's just put, now this is the sea level one, right? So let's put our wave in, blue, and we come down, up, up. Okay, that's what we do. And let's put it in up to there again and back down, like so, all right? Now there's a few very definite sort of things. This here we called the crest, and this is called the trough. Next crest, right? This is called the crest again. The top to the top. This is called the trough and the trough. Now what is important here is this term here we need to know. This is called the wave length, and it is given the Greek letter lambda. That is the length of a wave, all right? Like that. Similarly, this is also lambda. It's also a wavelength, isn't it? Right? It's a wavelength over there. In other words, here's another wavelength over there, right? The wavelength is from a point going in the same direction as to another same direction, one wave apart. In other words, the crest to the crest, the trough to the trough, where I'm going through the median, but here I am going downwards and here I am going downwards. Here is another wavelength, I'm going up and up. So that's my wavelength there from the up and the up. Okay? That's important from the first aspect. The second, okay, is this. We have to define another term. Right? Something that's very important is how big is this wave, right? Well, we come up and we define a term over here, and we call that the amplitude amplitude. It is, now be careful, okay? People have got different views as to what the height of a wave is, all right? But let's look at it like this. Let's say that is the total height from bottom to top. So if I'm sitting there, I say that that's going to be that. It's not defined as height, but the amplitude is there and there. So that height is equal to 2 amplitudes. The amplitude is how high I rise from my mean or median position. In other words, if the sea level was there, I'm stationary, right? There we go. Now the amplitude is how much we go up to where we get there. The amplitude down is that direction like that, okay? So we've now got the amplitude, okay? Crest, amplitude, right? The last thing is that this place here, okay? I'll just call it that one. Here where it goes through 0 is called the rest position. Why is it the rest position? Because that is where the particle is stationary, isn't it? Let's assume we've got a wave going along. It lifts us up. We were stationary. Now it lifts us up, brings us back to rest, and then down and back to rest. The rest position is where it goes through the mean or median of the wave. Okay? So we've just basically, like we did in other subjects, we're just putting down the whole vocabulary that we're going to be needing to do these problems, right? Now, in those we look at that. Now let's have a look at our slinky spring. Our slinky spring, when we do a longitudinal, that's a transverse wave. Let's do a longitudinal wave. Let me just label this one as then the transverse here. Hey? This is our transverse. This is the C wave. Transverse wave. The next step is the longitudinal wave. The longitudinal wave is by applying a pulse in that direction. Can you see it moving? It's actually quite difficult, but if you look, there's quite a lot of sites that you could look at on the internet, which actually show you the photography of waves moving longitudinally, and they do it in like the time lapse where you can see it from here to move to back to there, going through the rest position, right? So let's just do a few definitions over here. This is there, then the spring opens up, right? Then it comes here and then it opens up again like that. Then it does that. This one is called a compression. It's where the slinky spring was compressed close together. This piece here is called a rarefaction. Okay? It's called a rarefaction. Now, similarly, this is one wavelength here. All right? This is one wavelength over there. Okay? Now, that's what we need to know here. Okay? Now, can you see we're going to start looking slightly differently here? Because the particle is moved, it was at rest, it got compressed, opened up, and moved back to rest. Okay? So it passes through a rest position. Similarly, from the middle of a rarefaction to the middle of a rarefaction is also given the wavelength of this particle. Okay? Incidentally, those are things like sound waves, whereas the others are transverse. Okay? Now, let's look at another word. Okay? Another definition of a word. Superposition. Okay? Superposition. What do I mean by superposition? I mean something quite straightforward. Have any of you ever perhaps been on the beach and you see the waves coming in and they're all the same, all right? And then you do what you never should do, you turn your back on the sea, and the next thing you're flat on your face. Because what happened was these waves came in, but all of a sudden the wave suddenly got higher and it smacked you over onto your face. Okay? That happens often. That's why you never turn your back on the sea. what actually happened is this. You got another wave coming in and adding to that wave. Okay? Superposition is actually the adding of wave amplitudes. So, if I've got a wave traveling along in this direction, and this wave pulse is like that on a piece of string, then I say to you, all right, I do another wave on the same piece of string going this way, and it's got the same height, the same amplitude rather, let's call it that. What happens when these waves meet? Here they come, here they come, here they come. Okay, now, what happens now? Now it cancels it out. So as these waves meet, what have we got? We've got the wave above over there, right? So this one wants to lift the particle that way. What does the blue wave want to do? The blue wave says, no, 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 no. You must come here. So where does this poor particle on this wave want to? Well, it can't be there because that one says, no, you must be here. The poor particle, all it does is, in effect, it says, nope, I am just going to stay where I am because you and you cancel me out. Let's just look here. The blue here, A, cancels out the black A. Because the A is the same value, it cancels out, right? So the string doesn't move. As the waves pass, it just goes dead, and then the wave goes on after that, right? So after it's passed, okay, what have we got? We've got the black wave continues that way, and the blue one continues that way. Okay? And the piece of string goes up and there it goes down. So when they get together, it cancels out. Now what if we said A was 2 meters and blue A was 1 meter amplitude? What is the wave over there going to be? Well, it's actually logical. The wave over there is going to be 1 meter upwards that way, isn't it? Okay? It's going to be 1 meter up. It's going to be up like that. Okay? So the principle of superposition of waves, okay? These are definitions that you've got to learn. What is the length? What is, wavelength, amplitude? We're going to get to frequencies and things like that now. But let's have a look at another term here, okay? Yep, we'll have a look at another term. Let's look at the word interference, okay? Well, you know, you've often used this word, probably or possibly out of context many times. When waves interfere, for those of you who have a radio not exactly tuned in, right? You can hear another station in the background of yours. The two are interfering, right? Waves that come in the sea, these waves are coming at us like this, and this wave starts coming this way. They start interfering with each other. It's the next logical add-on from the superposition, because we don't just have one wave, we've got a whole series of waves coming at us, right? So these waves, they interfere with one another, all right? And the interference causes some very interesting patterns that we're going to be talking about, right? For example, okay, you get, let's have a look. Let's see what happens with this. Remember we said we've got that wave there, and we had our blue wave down here, right? Okay? Same piece of string, right? What happened here? There was interference, wasn't there? There was interference. The interference, the result was no wave. No displacement of the particle. The particle stayed right there. Remember I had it in green? Let me just put it in green. The particle stayed just there because the two cancelled each other out. Right? Now, that means that those two particles are actually, they are cancelling out. So we say that that type of interference is called destructive interference. Destructive because the one is destroying the other one. It's cancelling it out, right? Well, what happens then if we said, all right, we've got a wave going this way with an amplitude A. Now, you know what I'm going to do, don't you? I'm going to draw the blue wave coming along and amplitude A going that way. What's going to happen? Well, these two are going to join, aren't they? So the net result is going to be a wave that does that. It's going to be A plus A. It's going to be 2A. So the one wave builds on the other. It builds on the other wave, right? And guess what we call that? Yeah, constructive interference, right? Constructive interference is this one. It is constructive interference. It builds up a wave. And the other one was destructive interference. What does it do? It cancels out a wave. Destructive interference, we say that they are out of phase. Okay? And yes, constructive, we say that they are in phase. Okay? So there's a few more terms that we've just learned. So we say in phase means constructive interference. Okay? Builds up. Okay? Out of phase, destructive interference, it means cancels. Whoops. Let me just spell that a little clearer. Cancels out. Okay? Out of phase, they cancel out, etc., etc. All right? The last part, we're almost done with this bit. Okay? The last part is the period. Whoops. Is the period of the wave. Because one thing we've forgotten is not period. Okay? The period of a wave, we need time. The period is the time. Okay? The period is the number of waves passing a point in a given time. Okay? Period is measured in, okay, we'll get to that now. Okay, it's obviously the number of waves passing a fixed point in a given period of time. We actually look at it as per second, right? So it's going to be waves over seconds, right? Number of waves per second. That's what we do. So if you're standing at the end of a pier watching the waves go past, you can work out the period. You count. Hang on, how do you count number of waves? Hold on. You count the troughs passing you, or the crests. The crests are easy because it's normally the white water on top, right? You're looking at that passing you. So you're saying each and every crest that's passing me, there we go. So I say 1, 2, and then I count the number of waves and divide it by the total time. So if 12 pass me or in 60 seconds, my period is 1 over 60, right? So number of waves, let me rewrite it. It's number of waves over time. and it's waves per second. The last piece of information here, okay, is the frequency. These are all things that you'd have picked up when you're talking about waves. You're talking about radio. You listen to a radio station on so many, right? Megahertz or kilohertz, okay? The hertz is a measure of frequency. Okay? The hertz is a measure of frequency, and in fact, it is, your frequency is F is 1 over time, which is your period. Okay? It's 1 over your period. Okay? So, what does frequency mean? Frequency could be, for example, how many times I'm hitting. Like that. That's giving me a frequency of so many hits per second. Okay? In that case, it was maybe 2 hits per second. Much more. That's like 6 or 8 hits per second, right? And that's a frequency. How many times per second it's hitting. These are going to be when we're doing mechanics in ticker tapes. That's where it's coming in, okay? So it's good. I have gone way over on this one. My apologies for that, but I wanted to get out of the way this so that we can start some of the other parts, the rest of it. Okay, we're going to move on in the next one, and we're going to talk about pitch, we're going to talk about intensity, etc., and do a few examples. Thanks, and we'll see you in Physics 2, Session 2. Thank you.